So questions that you're going to see on your final exam. And as always, I reserve the right to reverse a question. Oh, they gave me this, and go backwards. And I'm just going to try and brush cobwebs off and give you highlights, details. You have a final exam review. You have my tutorials. You have each of the ultimate reviews. You can go through those as well. So certainly you can expect a projectile at an angle. Let's suppose we had an angle theta of 40 degrees. And let's suppose that this velocity here was 125 meters per second. And I said to you, find the range. How would we do that? Just come in, hurry up. Sorry? Even before I do a T-chart. Do I see angles? So? Oh yeah, do that first. So the first thing that I would do is I would find the horizontal and vertical components. I would probably draw this a little bit larger so that I can see what's going on. 40 degrees, 125. Turn your phone off, whoever that was, please. Here's Vx. Here's Vy initial. Why did I put an initial on the Vy and not on the Vx? Vx doesn't change. Vy does change. This is going to be opposite, hypotenuse, adjacent. I think we noticed that Vy ended up being sine and Vx ended up being cosine in this situation here. So in the interests of time, just to save time, here's my t-table. I think for you folks, I was writing horizontal and vertical, and I just decided with my physics 11s, why don't I put x and y there, because that's what I'm calling them, x and y. Don't even get in. Let's just go. Come on. I don't have time to waste. Everyone, YouTube's going to wonder who I'm yelling at. So, what are the two no-brainers that I can write? No, I can't write a equals 0. I can write ax equals 0. And? Okay. Those of you that showed up late, get out your formula sheet, get out your calculator, get a piece of paper here. And don't let me see your phones at all. What else do I know? Now, the rest I adjust based... I need more space. Hang on. I think I can do that. Insert. I have it here, Mr. Dewick. Yeah, there it is. Space. Move down. Okay. The rest I adjust according to the question. So in this situation here, I can say that Vx equals 125 cos 40. And I can say Vy initial equals 125 sine 40. And I'll calculate each of those quickly. Just move in, hurry up. So 125 sine 40. I get 80.348. I'll keep some extra sig figs. Try and follow along on your calculator. It's a good way to participate. How many things do I have in the left-hand column, Jaden?
2.
How many on the right-hand column?
2.
I need 3 things. What else do I know? What else do I know?
V final?
What's V final? First of all, X or Y, please?
Y.
Because I asked you to.
Yeah.
Okay. Come on, you'll miss that joke. Okay, what's VY final?
Negative 80.3.
Thank you for not saying 0. My last class said, isn't it 0? And then I said, well, do a belly flop onto the cement and tell me it's 0. It's going to hurt. What's VY final when we hit the ground?
Negative 80.348.
Which column do I have 3 things in now? What am I going to spend most of my time finding? Okay, so now I can find time. In this case, I think I'm going to use T equals VF minus VI over A. I'm going to end up going negative answer button. I happen to have this stored on my calculator. Minus answer button divided by negative 9.8. Good to see all of you typing along with your calculators and following along. Get my hint. I don't want to see empty hands here, please. Thank you. Do you get 16.397? No, yes? Yes. 16.397 seconds. How does that help? Well, if I want to find the range, I can now move time into the y column. The range is going to be dx. How can I find dx? What happened to the half at squared? Oh, good. So Vx is 125 cos 40. If you know what, why don't I just type that in instead of crunching it? 125 cos 40 times answer button. That works great. And I get a range of 1,570, yes? Good. What else could I ask? I could ask how high this goes. Maximum height. What does maximum height imply? Vertical or horizontal? Vertical. What do I know at the top? Vy is final is, for a split second, it's 0. Okay? That's about what I can ask for projectile. Well, I could, very basic, and I'll even tell you this question is on your test. I'm going to give you a projectile on an angle and just say find the components. That's on your test. And I'm hoping that's as close as we come to like free marks. I'm hoping everybody can find horizontal and vertical components. Okay? Nasty would be asking you to find the velocity along the way. I don't believe I did that on this. I assessed you on that in your unit test, but not on the final. We could also do horizontally from a cliff. We could also do horizontally from a cliff. So the key idea when we launch horizontally from a cliff, let's suppose that we have this velocity here is 30 meters per second, and let's suppose that this height here is 48 meters. In my t-table, what are my physics no-brainers? What can I write? Good. What's Vx? What's Vy initial? 0. Kids want to always use that 30. No, for a split second we haven't started falling yet. That's key adjustment number 1. Key adjustment number 2 is, what's dy? It's not 48. Yes. And now you can find time. Or I could give you the range. I could give you dx. That's way easier because to get the t by itself is much more simple. In this case, to find time, you'd end up going the square root of 2 times dy over ay, I think, if you run the numbers. Then from that, once you have time, the question falls apart. Then you can find whatever you need to find. Okay? So there is a question where I gave you horizontally from a cliff. I might have simply, as a multiple choice question, just said find time. Or I could have said find the range if I wanted to add the one extra step. Or I could have given you the range and said find the height if I wanted to add that extra step. That's a really quick review of projectiles. How do I add two vectors together? How do I subtract two vectors? First of all, I don't. What do I do instead? Add the opposite. So subtracting vectors, if you give me, vector A minus vector B, we'll just make a general one, that's the same as vector A plus the opposite of vector B. So if vector B was originally pointing north, how would I draw it if I wanted to draw it in the opposite? And then I can turn it into an adding question. How do I add two vectors together? Draw them to tail. All right. Forces. We're blazing. I think I can do that. There we go. So you can definitely expect something like this at angles. Those of you that got here late, the reason I'm not having you write stuff down, I'll print this up for you, or I'll email it to you, or I'll give it to you during Flex, but I want to fly. Let's suppose that this mass is 12 kilograms. Now, if this mass is 8 kilograms, which way must this accelerate? Which way must M2 be moving? Up the hill or down the hill? Up the hill. Now, if this mass is 40 kilograms, I have to do some number crunching because I'm not quite sure. M2 might be so heavy that it's able to pull down the hill and lift up M1. But let's make it, again, 8 kilograms, and let's put a coefficient of friction there of 0.76. What could I ask you to find? I could say Really, I could say find the acceleration, but in order to find the tension, we have to find the acceleration anyhow. So, heck, let's do the whole shebang. What am I going to do? What's this a job for? What are the forces acting on M1? Get the obvious one. I got to be fussy. Is there more than one mass? I'm going to call it M1G, right? Right?
Yeah.
What else?
Tension.
Tension. Like you're feeling right now if you showed up late. What else? That's it? Okay, now we move to M2. What are the forces acting on M2? Get the obvious one. I've seen all sorts of nonsense the past few days with people looking at this. I've seen people write gravity perpendicular. No. Gravity is still straight down. We did this. I also yelled at you. I said, make it a big long line, make it a big triangle. And then I also said, we always put the mg next to, on the same side as the angle theta. Haven't given you an angle theta yet. Let's make up an angle. How old are you all? 18? 18 degrees. We also said this, Linnea, that angle and, oh, what did we do as soon as we drew M2G? What did we do before we did anything else? What was our next move?
M2G perpendicular.
We broke it into components. Good. So we said this is going to be M2G perpendicular, and this is going to be M2G parallel. I used dotted lines to indicate those weren't actual forces. They weren't separate forces. I was taking the force on the free body diagram, mg, and just breaking it up. And we said that this angle and this angle were the same. We proved it once, and then we said as long as we always draw it that way, we're good. What else?
Normal force.
The same size as M2G perpendicular. I'll call it normal force number 2 to go with mass number 2. Okay. What else?
Tension.
Which way? Oh, on the rope. What else? Friction. Which way? I'm pretty sure this is, I know this is sliding up because it's a smaller mass than that. Now, if this was 40, I wouldn't know which way this mass was sliding. I wouldn't know which way to point friction. What I would quickly do is I would crunch that. Whichever one of those is larger, that's who's winning. But for now, Paige, I know that a larger mass hanging straight down has more oomph, has more force on it than a smaller mass on an angle. So I'm pretty sure that friction is going to be acting. In fact, I'm positive that friction is that way. What's my equation?
M1G minus MGT parallel minus force of friction.
I'll put those in there. You don't have to, but I often do just to make sure I haven't missed anything. When I did this in my last block, I'd forgotten to write that tension, and I caught it right away because my tension didn't cancel. And whoops, better make sure I add that. Minus M2G parallel minus, and you know what? I should have called it friction force number 2 to go with mass number. Thank you. Equals.
I'm all right.
Says find tension. Uh-oh. I have a tension deficit disorder. I've lost my tension. We're going to find acceleration, and then we're going to go look at one mass. By the way, I'm probably going to find tension with this mass because it's way less complicated, even though tension isn't the winner in that mass. I don't want to muck around with this ugly. I could, but why bother? So, how am I going to get the A by itself?
Flat over M.
It's going to be M1G minus M2G parallel, M2G 2 lines. Minus, I'm going to cross out friction up there for a second because friction is what times what? So I'm going to replace it up there with mu times normal force number 2. I don't know normal force number 2. Oh, but look. I know the force the same size as normal force number 2. Yeah. By the way, they just released the new physics curriculum. Next year in Physics 11, all of this with angles is now Physics 11. Dumb. I got to go on an epic rant. M2G perpendicular. Which trig function is perpendicular? Of course it is. Let's see if we can be bold and go to numbers here. So I'm going to go see on my calculator. I would type this as bracket 12 times 9.8 minus 8 times 9.8 sine 18 minus, what's mu, 0.76 times 8 times 9.8 cos 18. Yep. Close off the top, divided by, and I'll be brave, I'm going to go 8 plus 12 in my head, 20. What's my built-in error check? What's the maximum acceleration that I could possibly get here? Yeah, if we cut the rope, it'd be 9.8. So I know the answer better be less than 9.8. Did we all get 1.835? Okay. And I figured it'd be fairly small because 8 and 12 aren't very far apart. They're almost in balance. In fact, if I had identical masses hanging straight down, they wouldn't go anywhere at all. So I figured this would be pretty close. 1.83526, I'll write 1.83, but I'll keep this on my calculator. Sorry, 1.84, but I'll keep this on my calculator because this question said find tension. How would I find tension? I'd use this one because it's cleaner. What's my equation here? Good. And just M1A, one mass. Swappy dance. And we get tension equals M1G minus M1A. M1 was 12, and I have A on my calculator, so it's going to be 12 times 9.8 minus 12 times answer button. Whoop. And I get a tension of 95.6.
Yeah.
Now, a little note, on your test, it's multiple choice. Most of the time, I went to 2 sig figs in my answer for various reasons. Among other things, it just took up less space, it gave you more room, it makes wrong answers look less obviously wrong. Sorry, but I got to mess with you a little bit. So how would I write that?
95.
No, to 2 sig figs. How would I write that? Okay, so please don't, Mr. Dewick, I can't find my answer. It's there. Round off a little bit, please, okay? 96 newtons. What do we call this here thing? I'm going to tell you a question that you're going to see on your test. I'm going to give you a missing mass question. I'm going to give you a missing mass question. So let's suppose that this is 14 kilograms. And let's suppose that it's accelerating upwards at, let's make it a fairly big acceleration, 5 meters per second squared, which probably means this mass is pretty big. Okay? That's enough. I think we can do it. Let's find out. How would I start? Oh, heck yeah. What are the forces acting on M2? Get the obvious one. I'll go M2G because, you know, why not? What else? What are the forces acting on mass 1? And? Why wouldn't I want to go winner minus loser equals M all times A? I don't know M2. Okay. My strategy is going to be find tension, move the acceleration and the tension to this mass, and then write an equation for that mass. So let's write an equation for mass 1. Who's winning? I get a tension of 14 times 9.8 plus 14 times 5. You get a tension of 207.2. Double check me.
Yeah.
Yes. You tried that, did you?
Yeah.
Now I'm going to write an equation for mass 2. Looking at mass 2, who's winning? So my equation for mass 2 is going to be M2G minus tension equals M2A. Are you ready? How many M2s do I have? How many would I prefer? Get them to the same side. M2G minus M2A equals tension. How many masses M2s do I have? How many do I prefer? So, be cool if there was a grade 9 mathematical operation. By the way, I hope doing trig identities, you also found that trick fairly useful. Yes? I knew what I was doing when I planted that seed. Oh, there's a sign in everything. I can factor it out. Oh, I got a much nicer expression now, right? So factor it out. I get M2 bracket G minus A equals tension. So it's going to be tension divided by G minus A. You'll get two possibilities. It'll either be tension over G minus A or it'll be tension all over G plus A. But I don't memorize what type is what type. I just solve it each time. It's going to be 207.2 divided by 9.8 minus, what was the acceleration? 5. Hoping for a fairly big answer. 207.2 divided by bracket 9.8, take away 5. Yeah, 43.2. Tato, if I went to 2 sig figs, how would I report that answer? Okay, just it'll be there. That's a really quick review of forces. There's going to be some questions about Newton's laws. If you're not accelerating, what's the net force? How can you not be accelerating? There's two ways. You can either be going in a straight line at a steady speed or at rest. Okay? Circles. It's going to be a car going around a corner. Horizontal. It's also going to be a banked curve or a ballistic or a conical pendulum. And I got one of those coming up too. But for a car going around a corner, this is where we tried various free body diagrams. We found the top view didn't work very well. We found what worked best is a front view. We found it worked best. Oh, I need to give you the question, Mr. Duick. Find the safe speed for a car going around a corner of radius, I don't know, 78 meters with coefficient of friction equal to 0. But you know what? Let's make it slippery. 0.36. Okay. I should also have added the adjective circular corner. Just to, most of you would include in when I said the word radius, but I have to be fussy. Okay. What was our free body diagram? By the way, here I'm giving you the radius and saying find the safe speed. I would have no problem giving you the safe speed and saying find the radius, or giving you the radius and the speed and saying find mu. You'll see we can get all of them from a certain point. The free body diagram that we drew, I did something like this. I kind of put a little axle right there as though that was going to be the center of rotation. We drew a picture of the car coming towards us. What I ended up drawing was the tires of the car, like that. And then I drew the front of the car. There's the grille. I even put headlights in. And I drew the roof. And that's as good as you'll ever see me draw anything. But then we said, okay, what are the forces acting on this car? Get the obvious one. And that allowed us to see mg nicely. Is the car sinking to the ground like quicksand? Is it flying to like Superman? What path is this car tracing out? So there has to be a force pointing toward the... Do I label that FC? No, that doesn't show up on the free body diagram. So here's the question. What force pushes a car around a corner? What's my equation? Friction is pushing me in a circle. Friction is what times what? I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. And that's why we drew the free body diagram in this manner. It allowed us to see all of the key forces. So I get mu mg equals mac. Wait a minute. Which version of A am I going to use here? Okay, now what if I, instead of telling you the speed, told you the time it took? Now for this question it wouldn't make much sense, but for Ferris wheel rides and roller coaster rides, I could also give you the period, and you'll use the other one. This one's going to be the v squared over r. Can semi-trucks and little Austin Coopers go on this corner?
Yeah.
Yes, they can. How would I get the v by itself? And then? You know what? I remember when we were doing these, often there was the square root of GR or some variation. There was a G and an R inside the square root, and then sometimes something else. So whenever I see that pop up, I kind of get a little smile. I'm pretty sure I'm on the right track. I've probably done this right. So we have V is going to be the square root of mu GR. And if I really quickly crunch that, mu was 0.36 times 9.8 times 78. 16, oh, that's not bad, times 3.6. Yeah, you can do this at 60 kilometers per hour. We have a fairly safe corner, 16.6. This is the key equation. Can you see here, Paige? I could give you V and R and say find mu. I could give you mu and V and say find R, times the R over, divide the mu G down there. This was for horizontal circles. What other examples were there of horizontal circles? There was the gravitron and there was the space station where you got artificial gravity. In both of those, you had a situation where you had somebody standing like this or laying down against the wall in the idea of a gravitron. But the key idea was, what path were you tracing out? There was a force pushing you towards the center. What was the force pushing you towards the center? The normal force was what was pushing you towards the center. Now, in outer space, that was it. And then we said the normal force is the fake gravity. So if you wanted 80% of gravity, you would, for your normal force, put in 0.8 mg. If you wanted half of g, you would put 0.5 mg. For the gravitron, we had little mg down, and we had friction pointing up. And we did some more with that. Then there's going to be some vertical circles. Roller coasters and Ferris wheels are the two main ones, or a string, a mass on the end of a string being whirled around in a circle. The difference between a roller coaster and a Ferris wheel, they're identical at the bottom, but they're different equations at the top. Why are they different equations at the top? For a roller coaster at the top, which way is the normal force? Towards the middle, because it's which way your head points. For a Ferris wheel at the top, which way is the normal force? Up. Okay, so here we have this thing here. Let's suppose I said something like this. Sure. If we are traveling, I'm going to make a really unsafe roller coaster, because when I did this last block, I made one that had negative G's and the people would have fallen to their deaths. So I'm going to make sure that they're not falling to their deaths. I'm going to give them a pretty good speed up there, but the G's are going to be tremendous and probably be fatal in the other way, but they're going to die no matter what. So if we are traveling 42 meters per second at the top, find the normal force. Or I could give you the normal force and say find V. Or I could give you, Sarah, the normal force and V and say find R. How are we going to do this? What's this a job for? What are the forces acting on the roller coaster at the top? Get the obvious one. What else? Yeah. Who's winning? What path are we tracing out? A circle. Where is the winning force always pointing then? Toward the... So what's my equation here? Normal force plus mg equals m, and I'm going to use v squared over r because they gave me the v. I could also have told you how long for the Ferris wheel, because the v is constant. I'll typically give you the period. For a roller coaster, because you are slowing down at the top and speeding up at the bottom, just lose that. Then what was I saying? For the Ferris wheel, for the roller coaster, I usually give you the v because the speed changes. Okay. mv squared over r plus mg. Does an m cancel? No. Why not? Okay, it would be canceling if I was trying to find the safe speed, because the safe speed is the same for little kids and for adults. That's why I don't have to step on a scale before you get on. But as adults now, you feel the G-forces way more than little kids. Little kids can go on all sorts of stuff because they have a smaller mass. They don't feel it as much. Oh, that's why you may find as you get older, rides that you enjoyed as a child, your stomach doesn't like anymore. Oh, is that okay? Question over there? It is minus mg. This is what happens when people show up late. They throw me off my game. Thank you. So let's put an m there. Let's go m equals 450. You know what? Let's make it a person. Let's make a rider. Let me know there. You know what? Let's give you average mass. 65 kilograms. Okay. So if we really quickly crunch this, we're going to get 65 times 42 squared divided by 12 minus 65 times 9.8. We get a normal force of that. Newtons. If I want to convert that into an acceleration, or if I wanted to, well, first of all, I could convert that into kilograms. If I divide that by 9.8, this person feels like they weigh 910 kilograms, which is not very healthy. Or if I divide by their mass and then divide by 9.8, yeah, they're pulling 14 Gs. I'm just impressed that it worked out evenly. That's a nice fluke. This would not be a safe ride. Okay. What about at the bottom? Now, we did do a question, by the way, with roller coaster loops where we calculated the minimum R to safely make it through the loop, and it was really cool. Like, I think we got an answer of something like 2.5 times the radius or something like that. I'm not going to throw that at you, but certainly at the bottom would be fair game. So what could I ask you at the bottom? I could say, find the normal force at the bottom. Now, I'm going to make up numbers. So let's suppose if we are traveling 54 meters per second at the bottom, find the normal force. I'm just going to get it started. This is, again, a job for a free body diagram. What are the forces at the bottom? Get the obvious one. What else? Why did I draw normal force so much bigger? How do I know it's winning? What path are we tracing? Okay, so we're going to get normal force minus mg equals mv squared over r. And now, Linnea, it will get plussed over. Where do you feel heavier in a roller coaster? At the top of the loop or at the bottom of the loop? Thank you. Sorry? Why? First of all, what do you feel as weight? You don't feel mg as your weight. No. Yeah, you all feel your normal force. Okay? I went on a big rant both last year and this year. All amusement park rides do is they muck around with the normal force. They can't muck around with gravity. The technical definition of weight is mg, but we also call the normal force the apparent weight. Remember the OK Go video I showed you last year where they were experiencing no normal force and they were apparently weightless. They were in free fall. So this is what you would feel as your weight as well. That's why earlier when I did the artificial gravity, I said if we're talking about artificial gravity as weight, we're not talking about mg. What force are we talking about? Normal force, because that's what you feel as your weight. And we could crunch this and get an answer. That's a really, really quick review of vertical circles. Hey, we're doing good. Oh, insert space. Got more here, don't I? Yes. Oh, another horizontal circle. Yes, I do. Let's do a banked corner. So, find the safe speed if the angle is 26 degrees and r equals I'm just making up numbers. This could be terrible. This is what happens when I make up numbers. 91 meters. Why was the banked corner so nice? When we actually looked at it, we noticed that friction was not a part of this question. The banked corner would work perfectly. If you hit it at the safe speed, you can go around that corner even if there's ice. This is why they bank corners on racetracks. In fact, if you went too fast, you'd slide up and off the corner. If you went too slow, you could slide down the corner. You want to hit it just right. Now, how do we do that one here? This is a job for a free body diagram. What are the forces acting on this race car? Get the obvious one. I'll put the mg on the same side as the angle theta. Stop. Oh, no. Actually, this one we didn't go components. Really, Mr. Duick? We didn't. What else? And the reason we didn't here is because this time we want everything to stay horizontal because it's a horizontal circle and we want to go back to our horizontal frame of reference. It was easier when we were on a ramp earlier to tilt everything to the ramp. Here it's not. Those are the only two forces acting on this. I need to combine them. How could I combine them? Not add the opposite. I'm not subtracting. I want to add them together. How? Yeah. I get this. mg. How did I know to stop right there? What path is this car tracing out? And so the net force has to be pointing, the resultant has to be pointing toward the, I know that the resultant FC is right there. And we also noticed that angle theta ended up down there. Which trig function can I use? I'm going to ignore the normal force. I don't know the normal. I could probably figure it out, but who cares? Which trig function am I going to use for this? FC is opposite. MG is adjacent. Care to revise your lousy guess there, Tato? Which trig function? Opposite over adjacent. Mr. Duick, I don't know the mass. In fact, I think on your test I didn't give you the mass either, and people freaked out. First thing I'm going to do is I'm going to get the FC by itself. So rather than writing it that way, I'm going to go like that. Which version of FC, you know what, Mr. Duick, since you're going to rewrite it and kids are going to be looking at this, let's bring it back there. And then now let's rewrite it. I'm going to get mg tan theta equals, which version of FC am I going to use? Because they said find the safe speed. Why didn't I need to tell you how heavy the car was? Could you get the V by itself? Do you notice once again we're going to get a square root of GR and other stuff, but I'm on the right track. So if I crunch this, Mr. Duick, I'm going to get V equals GR tan theta square root. And you'll notice no mu. I'm able to do this without friction, which really means friction can be 0. If I wanted to make this nastier, I won't. But if there was a coefficient of friction, what that really does is it gives you an upper-lower bound for the speeds as well. This is the bang-on perfect speed. If you include friction, you can add it in your free body diagram and you can figure out what's the fastest I can go before friction can't hold me from sliding up. What's the slowest I can go before friction can't prevent me from sliding down. We didn't do that. I'm certainly not going to ask that. But if you're wondering, we could. It's not that much harder. 9.8 times, what did I say the radius was? 91. Tan 26. Square root of that. 20.8 meters per second. About 70 kilometers per hour, maybe a bit more. 20.9, Mr. Duke. Once again, Sarah, from this line right here, could I instead give you the safe speed and say find the radius? Heck yeah. I guess I could, well, finding G would be pointless because it's 9.8. So I guess I wouldn't do that. Okay? No, I decided, I think we did one like that on the homework, but I never put it on your test. I might next year, but right now, no. Gravity. No yawning. You fail to realize the gravity of the situation. Okay. We said that we were talking about, or first of all, we have our universal gravitation equation. I'm going to ask you stuff like, if the gravitational force is 12 and one mass is 6 and we're this far away, find the other mass or find the radius. Be able to rewrite this equation and get any of those by itself if I give you the rest of it. That's fair game. But then we went to orbits and rocket science. So if a satellite has an orbital period of 12,000 seconds, find the orbital radius. How would I do that? Gravity is what's pulling me in a circle. In fact, any time that I was in orbit, that's almost always my first starting point right there. Then gravity is big G, big M, little m over r squared. And this is going to be MAC, except instead of writing AC, I'm going to put an expression for acceleration. Which version of the circular acceleration am I going to use here? Okay. By far, the most common mistake, kids would forget to put the little m there because this looks like a force because it's so complicated looking. But the problem is if you don't put that m there, you're going to be in trouble because why? Yeah. Once you're in orbit, little m cancels. When we calculated how much energy to put stuff in orbit, the mass didn't cancel. Of course, it takes more fuel to put the space shuttle in orbit than it does to put a little satellite in orbit. But once it's up there, keeping the ISS up there, no problem. We're going to get the r by itself. Oh, and r cancels, yes? There was one version, typically when we had the mv squared over r here, then an r canceled, but in this one an r does not. That was sloppy mistake number 2. Thank you for being predictable. Instead, we said if you multiply the r squared over, we get an r cubed. We get an r cubed. We get a big G, big M. We multiply the t squared over. We divide the 4 pi squared over. I always love this because, holy smokes, how do we get rid of a cubed? We finally had an actual use for cube root. Big M is going to be the mass of the Earth. You can assume we're on the Earth unless the question blatantly says otherwise, if it talks about the moon or another planet. But I think I kept us earthbound. So if I go to my calculator, then what was big G? Oh yeah, this was the unit where we were typing like crazy because the constants just weren't convenient. So we had 6.67 times 10 to negative 11 times mass of the Earth was 5.98 times 10 to the 24th times 12,000 squared divided by bracket 4 pi squared. And then I got to cube root that baby. For me, it's math, option number 4, answer button. And I get an orbital radius of that. I was making up numbers. I hope I'm not inside the Earth because the radius of the Earth is 6.38 times 10 to the 6. 1, 2, 3, 4, 5, 6, 7, 8. Oh, lots of breathing room. We're way out there. Good. Trying to give myself some breathing room. I know the International Space Station orbits roughly every 90 minutes, so I just wanted to make sure that this was more than 90 minutes, which it is. 1.13 times 10 to the 1, 2, 3, 4, 5, 6, 7. What if I asked you to find the orbital altitude? What would I do with this orbital radius? So if I wanted the altitude, don't give me any altitude, 6.38 times 10 to the 6th. That there is the altitude. I'm going to go back to the radius because I want to use this. So I'm going to add 6.38 times 10 to the 6th back to this, please. There's my radius again. What does B want me to find? Okay. There is a question where I don't do part A, where I just do part B, and I expect you to clue in. You need to find the radius to get there. I either give you the orbital speed or the orbital period, and I say, tell me the gravitational field strength. First of all, what is gravitational field strength? What's the equation for gravitational field strength? It's sort of on your sheet. How can you get that? Look up, Linnea. Gravity equals gravity. The shortcut equals the universal one. What do you notice about the little m's? There is your universal expression for gravitational field strength. That'll tell you the gravitational field strength anywhere in the universe. And so if we're finding it here, it's going to be 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, divided by answer button squared. That's an A and S squared. What's my built-in error check? I know it's less than what? Yeah, we're way out in space. It's going to be less than 9.8. I'm guessing, is it in the 3s or the 2s? We're far enough away that it's still not negligible. Okay, that was a total guess, but I'll take it. So, what was it? Sorry? 3.11. Units? No. I would accept meters per second squared. What's another way to measure gravitational field strength? Because we noticed fields often had two different ways to measure them. Newtons per kilogram. Because if it's an acceleration, isn't any acceleration force divided by mass? Mm-hmm. Yes. I usually use newtons per kilogram when we were talking about gravitational field strength because I like to think to myself, oh, every kilogram feels 3.11 newtons of force acting on it. Gotcha. Okay. Why, when we're in orbit, why are we floating if there's gravity? Why do the astronauts float on the ISS if there's gravity? Because the ISS, I think we calculated it, their gravitational field strength was like 9.2 or something like that. Almost like the Earth. Why are they floating? They're in free fall. So make sure you understand how orbits work. An orbit is not floating. An orbit is, this is why it's so expensive to put stuff in orbit. Not only do you have to give it enough potential energy to get it to the right height, then you still have to have extra rocket fuel to give it kinetic energy to keep it in that stable orbit. In fact, that leads us to part C. We can find the orbital speed. How could I find the orbital speed? I said orbital. That's your hint. Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals, this time I'll use mv squared over r. And I still happen to have r on my calculator. If not, I would quickly recrunch it. I kept mine here for a reason. Sorry for those of you that use it to find the 3.11, but we'll keep this there. In fact, this is the one that we did an awful lot. Tato, does an R cancel here?
Yeah.
Oh, okay. In fact, we found that V orb, some of you even had this memorized at the time, it ended up being that. So if I want the orbital speed, it's going to be 6.67 times 10 to the negative 11 times the mass of the Earth divided by, I still have this stored on my calculator, thankfully, square root of that, and I get 5933, almost bang on even, I'll take that, 5,933 meters per second. What else could I ask about orbit? Oh, find the total energy. Okay, so we had these weird energy equations for orbit. We could no longer use mgh for potential energy. Why couldn't we use mgh? Sorry? Yeah, g changes. So we had to define it somehow. We said that we're going to define 0 to be relative to infinity. All the way out at infinity, that's when you have 0 potential energy. If you're closer than that, you have less than 0. Negative. So that's where we had this cosmic potential energy was negative big G, big M, little m over r, not r squared. So if I wanted to find total energy, I guess total energy would be, yeah? Hey, let's find the KE. Why am I doing the KE? Because I happen to have V stored on my calculator right now. KE is going to be a half mv squared. Little m, uh-oh, they didn't give me a mass, so I've got to go all the way back here, and I'm going to have to add, and mass 3,500 kilograms. There, now we've got a mass. So if I crunch that in a hurry, it's going to be 0.5, 3,500, almost exactly 5,933, but I'll use my answer button. Don't forget the squared, Mr. Dewick. I can't believe I did that. I have a student in my Block H class right now who will be laughing at me. Do you get 6.16 times 10 to the 10th? Yeah? And I recall a lot of our answers for these were 10 to the 10th and 10 to the 11th, so I also feel pretty... Once in a while, 10 to the 9th, not often. Once in a while, 10 to the 12th, not often. I'm pretty good about that. So 6.16, Mr. Dewick, times 10 to the 10th joules. How can I find the potential energy? Negative big G, big M, little m over R. Negative 6.67 times 10 to the negative 11. This is where we often started using ditto marks and things when we were calculating work, because work was a change in, and you ended up writing this thing twice very often. 5.98 times 10 to the 24th. 3,500 divided by, do I still have R? Oh, I wish I had R. I didn't write it down to very many sig figs, and I should have. I'm trying to find it back. So it was that thing, and then it was the cube root of that. 11331218. I'll get a negative answer. You get negative 1232 times 10 to the 11th? No, yes, yes?
Yeah.
1.2, did I say 1232? 1.232 times 10 to the 11th joules. So what's the total energy? Add them up. And if we're lucky, you'll notice we could have saved ourselves a lot of time. Because when I add this to 6.16 times 10 to the 10th, I get, I'm going to guess, negative 6.16 times 10 to the 10th, do I? You might recall we noticed as a neat little handy pattern, for what it's worth, the kinetic energy and the total energy were the same number, but the total was negative, the kinetic was positive. And we noticed that the potential energy was twice as big as the kinetic, but negative. And we mucked around with just doing some substitution, and we just noticed that pattern. I did say, Sharon, you can survive just fine without it. We did, but the fact that this happened now, I'm pretty sure I'm right with all my previous steps, because how could I have fluked into that lovely pattern? That is a real quick review of gravity. After gravity, we did electrostatics. I got 10 minutes left. Do you want to give it a try? Okay. Questions you might see. Find electric field. 4.6 microcoulombs. Negative 1.2 microcoulombs. Better yet, let's make this one no, let's make, you know what, let's make both of them negative. Let's have some fun. And let's make this distance 2.4 meters, and let's put a little location right there, x, and let's call that 0.8 meters. Find the electric field at location x. That's a real quick sketch. I didn't think I'd get this far, so I didn't have questions pre-planned for this far. You guys have done well, aside from many of you showing up late. How am I going to do this? By the way, I guarantee this is on your test. No. Oh, I have an equation for electric field, do I? First thing I think I would do is I would call this Q1 and Q2, because why not? I've taught you to be organized. So I'm going to find the electric field from charge 1, which is going to be KQ1 over R1 squared. It's going to be K. What was K? A much nicer constant than 6.67 times 10 to the negative 11, but it's the universe we got. Change it if you can, but it's the universe we got. Am I going to put the negative in? If it was voltage potential, I would. If it was energy, I would, but not for forces or fields. So it's going to be 4.6, what was micro? Divided by 0.8 squared. And I get 64,687.5. What were the units for electric field? You can figure it out from your formula sheet. No, you can figure it out from your formula sheet. Look at the original definition of electric field, please. It's newtons per coulomb, because I think you have F equals QE, or do you have E equals F over Q? Yeah, it's newtons per coulomb. There was also a second one, volts per meter, right underneath it. I think it's right underneath it or right beside. Yes? Because it's also voltage divided by distance between plates. Direction. What direction is the electric field from that? How do we figure out direction? It's which way would a positive at location X want to move because of that guy? Which way would a positive right there want to move because of that guy? Because unlike charges, I've forgotten who I always picked on for that. We repeat, for charge 2, it's going to be KQ2 over R2 squared. It's going to be 9 times 10 to the 9th, 1.2 times 10 to the negative 6, and 0.16 squared. 0.16? That's wrong, Mr. Dewick. Sorry? 1.6, yes? My brain was bugging me about something there, and it just shifted into neutral for a second. I get 4,218.75. Direction. How will I add left plus right? Your winner minus loser. How would I add, what if they were both in the right direction? How would I add right plus right or left plus left? Just add them, okay? So this is going to be 64,687.5 minus that. The net electric field is that direction. Winner. Okay, we also did stuff between parallel plates. We found the electric field between plates. We found how fast charges were traveling between plates. That involved conservation of energy. We also did conservation of energy questions between points. We also did voltage questions between points. And I'm losing you, and I just don't have time to get to all of this. So electrostatics, you'll have to watch a video YouTube lesson on your own if you want to.